So hello everyone, my name is Ronny Almeida. I'm a civil engineering student at Universidad San Francisco de Quito in Ecuador. I flew all the way here, and my family is also here, and I am very, very grateful to have the opportunity to present what my partner, Juan Jose, and I have been working on for the past year. Also, my supervisor here is Francisco Hatiba, and today I'm going to talk about translucent concrete. The main objectives we have for this research were to obtain the compressive strength, the dynamic modulus of elasticity, and also the luminance of cement paste and plastic fiber optic in different volumes. For this, we needed to design the mixture. We also needed to design, make the formwork. So first, we're going with compressive strength. In the compressive strength, we used an acrylic mold that was designed using AutoCAD, and then we used a laser to cut the holes. We also, with this formwork, we have a total of 12 cubes, so we can perform the compressive strength test. The compressive strength test we use is the ASTM C109 that gives us the procedure to obtain the compressive strength of cubical specimens. Here we have the compressive machine that we used, and in the right we can see a test being performed. Here are the results we got. In the x-axis we have the current time, in the y-axis we have the compressive strength, in the left in megapascals, and in the right we have it in KSI. As we can see, in 90 days we see a drop in the resistance. If we add plastic fiber optic, the reduction is 42%. And we can also see that between 3 and 5% there's no significant difference in the change of resistance. Now, with the dynamic modulus of elasticity, we used a formwork that was designed using Inventor, and then we 3D printed so we can have a cylinder that lets the fiber go through its diameter. We also, after the casting, we cut it in discs so we can perform the test. Now, imagine that a drop falls into a calm lake. Once the drop makes contact with water, we know that it's going to generate waves. And we also know that the maximum displacement of the water is going to happen right in the point where the drop fell. This is the concept that Hutchinson, Lemming, Now, and Fukuda and Rashetnia used in the research to develop the theory that led to this test. The test consists in dropping a sphere into the disc. The disc is going to vibrate. To capture the vibrations, we're going to attach an accelerometer at the bottom, and the accelerometer is going to send the signal to the computer. Here we have the schematics, and we also have the setup that we used in our laboratory. In the left figure, that is time versus amplitude, we have also the signal that we received from performing the test. After putting this signal through the fast Fourier transform, what we obtain is the figure on the right, that is frequency versus amplitude. What we're looking for in this figure is to obtain the frequency where the amplitude is at its maximum. And this is one of the parameters that we need to calculate the dynamic modulus of elasticity. Along with the Poisson's ratio, density, diameter, and omega 0, we can calculate this parameter. We also wanted to see how the frequency changed if we use different specimens. So we started with steel. In this figure, we have the frequency in hertz divided by omega 0, and in the y-axis we have the amplitude. We started with steel that had around 19,000 hertz of frequency, and if we use only a cement paste mixture, we see a drop of 44% in the frequency. We did that also with 3, 4, and 5% of plastic fiber optic in the mixture, and between the control specimen and 5%, we see a reduction of almost 50%. Here are the results of the dynamic modulus of elasticity. In the x-axis, we have the specimens we tested. In the y-axis, we have the dynamic modulus in gigapascals. As we can see, the steel has the highest dynamic modulus, and between the control and plastic fiber optic specimens, we can see a drop of 78%. We also can see that between 3% and 5%, we don't see a significant difference in the dynamic modulus. Finally, with luminance, here the formwork was made almost the same as the one we use in the dynamic modulus, with the slight difference that instead of the fibers going through its diameter, it went through its length. We also 3D printed the setup so we can put the disc on top. the luxometer on the bottom so we can measure the light, and the lantern on top so we can see how much light was going through. And we also wanted to measure the illuminance in different weathers in Ecuador. So this is what we got, is what we have in the figure on the left. In the x-axis, we have the time between 7 a.m. to 6 p.m. And in the y-axis, we have the illuminance. We can see that around midday is where the illuminance is at its maximum, independently of the day and the weather. And we used as a reference a sunny day that had around 170,000 luxes of illuminance. In the right, we have the results. In the x-axis, we have the specimens. In the y-axis, we have the illuminance. And we can see that the specimens with plastic fiber optic had 2 orders of magnitude illuminance below the sunlight, being the maximum around 5,000 luxes. That will be equivalent to put a 50-watt LED light into a square meter. Finally, in the conclusions, we were able to achieve all the objectives we have from the beginning, and we also designed the mixture, we make the form works, and we also measure all the parameters we wanted. In the future work, we also want to see how the plastic fiber optic interacts with aggregates and also with the reinforcements. Thank you very much. That is